So I'm going to just kind of briefly walk you through how to do this, and then you can kind of go back on the video and look at this if you need to for the homework assignment. This is the exact same example that's in your book, so I'm just going to kind of talk you through it. So we've got a proposed culvert. We've got a design discharge that we estimated from a hydrologic model from the watershed. Okay, we did Manning's equation in the upstream channel. So it's we used heck rats, and we had a model of the stream upstream, and we figured out that where the road's going to cross the creek, the flow depth is 3.2 meters given this discharge. That's a pretty big discharge. It's cubic meters per second. We multiply that by about 35.1 to get cubic feet per second. So there's a lot of cubic feet in a cubic meter. The culvert's going to be 40 meters long. It's going to have this entrance. Here's the slope based on the topography. And based on our HEC-RAS model, we know that the outlet will not be submerged, or we want to design it that way. So find the diameter. So we're going to be a circular culvert here. Find the diameter. So the way to figure this out is, well, what kind of flow class do we have here? Is it A, B, C, or D? And that way we can know what equations to use, what energy loss, and do we have pressurized flow, full pipe flow, et cetera, et cetera. Well, okay, we know that it's not A because we said it's going to be, it might be submerged upstream. We don't know that yet, but we know that it's not submerged downstream, or we don't want to design it so that's not submerged downstream. So that's not going to be A. A was submerged upstream and downstream. Okay, could it be D, where we have no submerged happening upstream and no submerged happening downstream? Well, if the upstream flow depth is 3 meters, then we would need a diameter of about 3 meters. That's a really big pipe, and maybe that's going to be too expensive or something. So we're going to say, no, we're not going to do that. It's okay to have it submerged upstream. It's not the end of the world for this design discharge. So we're going to be somewhere with the B or the C. We don't know which yet. Is it going to be submerged all the way through the pipe or partially through the pipe? So let's just run the calculation through for the Class B flow calculation. Okay, so the way this works is we need to start with a datum. And our datum we'll call as the inverse, or the bottom elevation of the culvert at the downstream end. So that's going to be 0. Now, to figure out what this elevation is, we have to back calculate. So we have a slope of the bed, and we have the length of the culvert. So we can use the slope times the length to get the actual rise and elevation. So that's what this is. This is our Z value, slope times length. So that gives us this elevation right here. And now we need to add our normal depth on top of that to get the total elevation at the headwater. So normal depth, which we were given right here, 3.2 meters, and then the slope times the length of the culvert. Our tailwater elevation is going to be, under Class B flow, it's going to be the diameter of the pipe, because that's just the elevation off of our datum. It's going to be the diameter of the pipe. We don't know what that is yet. Okay, so headwater elevation is equal to tailwater elevation plus head loss. We can put in the slope times the length plus our normal depth for the headwater elevation. Our tailwater elevation is going to be D, and then our head loss we'll calculate. So now we can solve for D, so we can use this equation right here and solve for D. So D is going to be equal to the normal depth up here plus the slope times length. We get this headwater elevation minus head loss. So we can go do our head loss calculation, which is this big old crazy equation. D is in that as well. And what we end up with is plugging in this equation for head loss. We can say, we can just end up solving for D. So D is going to be equal to this is our head loss times this part, the discharge over D to the 4th, which we have this information from our design discharge. D comes into play down here with hydraulic radius, and we end up with D in a bunch of different places, but you can multiply this through, and maybe you need to use solver or something like that, but you end up with D is equal to 1.41 meters. So it's a little convoluted algebra, but really we're just using this equation right here, and then head loss has D down here in the denominator and D right here for head loss calculation. So you can follow those steps through and end up with a certain diameter. Okay, so this is if we assume that it's class B flow. We don't know yet. Let's do the class C flow, where we have basically this orifice flow, and it's controlled by the headwater elevation only. And we measure H, oh, okay. In this case, we measure H above the center line of the pipe. That's the way we do the orifice flow calculation. So we've got our pipe. We've got our headwater elevation. And this is H for orifice flow. Okay, so the way to do this calculation, we knew we were given that our normal depth upstream is equal to 3.2 meters based on the channel and the hydraulics there. And we know then that our diameter, so half of our diameter plus H, so this is D over 2 right here. So half of our diameter plus H is going to equal 3.2 meters. So that's what this equation is. And then we can solve for H. So our normal depth is equal to half diameter plus H equals 3.2 meters. H is equal to 3.2 meters minus D over 2. So we go to our orifice flow equation. Q is equal to the discharge coefficient times the cross-sectional area square root of 2GH. We plug in pi d squared over 4 for our area. And then we plug in 3.2 meters minus D over 2 for our H. So we know our discharge. We choose our coefficient based on that square entrance. And we've got D in a couple places. We can do some algebra and solve for D as 1.25 meters. So we've got two different Ds here. Is it going to be at 1.4 meters from class B flow or 1.25 meters from class C flow? Well, let's just choose the bigger one. Now there's one more check we can do, and we can go back to that figure 6.4. And calculate this ratio right here. So we've got D now from our estimate of 1.5, and I rounded up to 1.5 because maybe you can only buy a 1.5 meter culvert, maybe you can't buy a 1.4 meter one. So we do 1.5, we do Q, and we plug in all these values. So that's what I do right here. So plug in all of our known values, and was 0.024 for corrugated metal pipe. Here's our design discharge, our slope, our diameter. So we end up with 0.78. And 0.78 is not on this chart, so that means we are full on the pipe. That means the pipe, the normal depth in the pipe is greater than the diameter. And so even if we had a bigger diameter, right, of like 2 meters or 3 meters, maybe at some point, you know, we would have the pipe that wouldn't be full. So what this tells us is that our normal depth in the culvert is greater than the diameter, and that means we'll have class B or full flow throughout the pipe. That was just a little check we can do to kind of verify what the flow conditions are. But what we figured out was we don't have to get a 3 meter diameter pipe. We can do a 1.5 meter diameter pipe. It'll pass that discharge, and given this headwater elevation, or that depth of 3.2 meters. So we'll be okay. And as long as that headwater depth of 3.2 meters isn't going to overflow our road. And there's different design standards that people have of like how much of that submerged, how high the inlet can be submerged and stuff like that. So as long as we're within the design standards, we can do a 1.5 meter culvert, circular culvert, and move that discharge through.